Well, we start chapter 4 today. And this is your beginning of what we refer to as the wonderful world of integral calculus. So we're going to talk first about what we call an antiderivative, and then transfer that, kind of morph that into what we call an indefinite integral or indefinite integration. So chapter 4, section 1, antiderivatives and indefinite integration. All right, this is kind of like taking the derivative, as the name might indicate, antiderivative. This is kind of like taking the derivative in reverse. Instead of saying, here's a function, take the derivative, let's say, here's a function, what function would we take the derivative of to get it? All right, so that kind of makes sense. For example, it says, can we find a function, capital F, whose derivative is f of x equals 4x to the third? Well, if we try to think about this, we try to think of a function, call it f of x equals something, whose derivative, lowercase letter f, would be 4x to the third. So we're trying to reverse the process of taking the derivative. And this is called, as the name might indicate, the antiderivative of the function lowercase letter f. So by definition, the function capital F of x is an antiderivative of a function lowercase letter f of x if the derivative of capital F of x, capital F prime of x, is equal to lowercase letter f of x. I know you're getting kind of tired of me saying uppercase and lowercase. For all x that's in the domain of a function lowercase letter f. So what we're going to do is we're going to try to figure out what function we take the derivative of. Let's see if I can keep this on the screen. That would give us 4x to the third. Now I'm hoping that you're thinking maybe x to the fourth, just using the power rule. You bring the 4 in front, and then you subtract 1 from the exponent, and we would get 4x to the third. But somebody might else say, hey, wait a minute. Couldn't I take the derivative of x to the fourth plus 1 and get 4x to the third? So that's where this theorem comes into play. It's called the representation of antiderivatives. If f is an antiderivative of capital F is an antiderivative of lowercase letter f on an interval I, and g is an antiderivative of lowercase letter f on the interval I, if and only if capital G is of the form capital G of x equals capital F of x plus c for all x in the domain, or in I, the interval I, where c is a constant. So that's this plus 1 here. If I add 1 to it, I get another function whose derivative is 4x to the third. So they're saying there's more than one antiderivative. So since there is more than one, and they're all just by adding on a constant, we can kind of classify these antiderivatives by putting plus c, where c is called the constant of integration. So by using this theorem, we can represent an entire family of antiderivatives of the function. See, I have capital F of x up here is equal to x to the fourth, but I could also have plus 1. I could also have plus 11, plus 112. There would be a whole family. Graphically, they would be vertical translations of one another. There would be a whole family of antiderivatives of this function, and we represent that by putting down the constant, the plus c, whereas c, again, as I mentioned, is called the constant of integration. And the whole family of functions is called the general antiderivative of f. So that's kind of different looking. So instead of saying, what are we taking the derivative of, we're saying, let's take the derivative of this. I'm saying, what would we take the derivative of that would give us this derivative? Now, I'm going to define here, as we mentioned at the end of the last chapter, we were talking about differentials. I'm going to define a differential equation in x and y. All right, now differential equations, we're going to study them in this chapter a little bit. We're also going to study them in chapter 5. And for those of you that are going to become engineers, after you've taken the first 2 semesters of calculus, you will have to take, most likely, either after your second semester or perhaps even after your third semester, which is when I took it, a class called differential equations. And we're going to look at some very basic differential equations. It's a very complex field, but we're going to look at the very basics here in chapters 4 and 5. So we're going to start off with the definition that a differential equation in x and y is an equation that involves x and y and the derivative of y. And in some cases, it doesn't even have to have the y. It might just all be in terms of x. This is a differential equation. this is a double prime here. This is a differential equation. We would call this an order 1 because it's the first derivative. We would call this an order 2 differential equation. Now, to solve a differential equation means to find y. We write the equation in equivalent differential form, which means we take dy dx, for example, right here. We have y prime, which is dy dx equals 5x, and we would write it as dy equals 5x dx, which is the differential form from the last section in chapter 3. Then we would make sure our variables are separated, as in this case it already is. I got y's on the left, I got x's on the right, and then we would have to take the antiderivative of both sides and solve for y. So let me show you an example of that here. Before I do, let's look at using this idea to bring in integration notation here. If I have dy dx is equal to f of x, and I write this in differential form, and now I'm going to take the antiderivative. To take the antiderivative, you'll see I'm using a symbol which looks like a little bit like an elongated S. And this means that I'm taking the antiderivative on the left side, I'm taking the antiderivative on the right side. Now, the antiderivative is also called the indefinite integral, and that's this symbol here, that I'm taking the indefinite integral of dy and the indefinite integral of f of x dx. You can see why, I hope you can see why, we were using differential notation in the last section when we were taking derivatives. Now, this guy right here, I brought him down here. This is the integration sign or symbol. This part right here, not the dx, just this part that's in front of the dx, that's factor, is the integrand, and then the dx, this differential of x, is just there as notation to tell us which variable we are integrating with respect to. And when we do the antiderivative or the indefinite integral, the dx is kind of like a catalyst. It's used up in the process of finding the antiderivative, and it kind of just disappears, and that's where we get this plus c here for our constant of integration. Notice here, the antiderivative, capital F of x. The antiderivative of dy is just y. So what's now? All right, I'm going to find the general solution of each of these two differential equations. So I'm going to use the same process. I'm going to write this as dy dx equals 2x. I'm going to write it in terms of differentials. Dy equals 2x dx. And then I'm going to integrate both sides, or take the antiderivative of both sides. Well, the antiderivative of dy is y, and the antiderivative, now what function would we take the derivative of that would give us 2x? And I'm thinking, well, using kind of like the reverse of the power rule, wouldn't it be x squared, because the derivative of x squared is 2x. Now I'm going to write x squared, and I'm also going to put down the plus c. If you wondered, why do I put the plus c here and don't put plus c's on both sides? It's because if there was another constant over here, I could just combine it with this constant. There's no need to write it twice. And this would be my general solution of my differential equation. I don't know what my differential equation is exactly because I don't have enough particulars. Like if I had some more information about the x's and the y's, you know, like x is this when y is that, an initial condition, let's say, then I could go about and find out exactly what c is. But we're going to write it in this general solution form. Over here, I'm going to write dy dx is equal to 10. So that means dy is equal to 10 dx. I separate my variables. I integrate both sides. This is y. Now, what would I take the derivative of to get 10? And I'm taking 10x. And then plus my constant again. Now, if you take the derivative of 10x, don't you get 10? And that would be my general solution. So yeah, not all differential equations are this straightforward. Most of the ones that we will be dealing with in this class, though, we can separate the variables and we can integrate both sides and solve that way. Now, again, due to the fact that integration and differentiation kind of have they're kind of like inverses of one another, and there's a very important theorem that we're going to study later in this chapter that kind of ties these two ideas together, but we can use that to kind of like find some basic integration rules. Now we know that if we have the integral of f prime of x dx, that we would get the antiderivative, which would be capital F of x plus a constant, and yet if we take the derivative of the integral of f of x dx, we should get right back to f of x. Now notice here, there's the plus c. Notice here it's not, because you're taking the derivative and the constant would disappear. But here are some of your basic integration rules. If you're trying to integrate 0 dx, you just get a constant, just c. If you integrate a constant times dx, you're going to get that constant times x, because the derivative of x would be dx, and so you get that constant times x plus, again, your plus c here. Now here we can use the fact that it's called like a scalar rule, where we can bring this constant out in front times your antiderivative times your indefinite integral here. And here I have the integral of a sum or a difference is the sum or the difference of the integrals. And here, I'm going to put a little star next to this guy because he's important. This is your power rule for integration. Now we know that when we were integrating, like, or differentiating x to the fourth, the 4 would come out in front and then we'd subtract 1. Well, we're going to be adding 1 to the exponent, and instead of multiplying by that, we're going to be dividing by that new exponent here. So the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus a constant, as long as n does not equal -1. If n equals -1, then we have to use a different rule. It's not going to be a power rule. It's going to involve logarithms. And then we also have the antiderivatives. It looks like maybe I forgot one of them. I did. I think I forgot the, we'll put this as number 11. Let's see if I can raise this up a little bit. The indefinite integral of the secant of x dx, or actually the secant of x cotangent of x dx, which is the secant of x plus a constant. So here's the 6 rules for our trig functions. Now I know that this is cosine and this is sine, and we don't have one for tangent yet. We don't have one for cotangent yet. We don't have one for secant and cosecant yet. Just those functions by themselves. But we do have these that we could get from our derivative rules that we had earlier on for all 6 trig functions. It's just kind of reversing the process. You need to put these to memory. There's a lot to keep track of, but you need to put these to memory. And let's practice some with some examples. All right. Let's integrate 5x dx. Now, the integral of x, here, let me put it right here. The integral of x is x to the first dx is the power rule where you add 1 to the exponent. So this would be x squared all over the new exponent, and then your constant. I have a 5 that's times that. So this is the same as 5 times x to the first dx, which is 5 times x squared over 2 plus your constant, which we would write as 5/2 x squared plus my constant. Now it's going to take a while to get used to this, but you don't have to sit there and say, okay, what am I going to do? What would I take the derivative of to give me x to the first? You're going to use the rule, the power rule that I just gave you, and you can find that function. Now, I don't normally write this step in. I usually go from here to here, or to here, because I've practiced this enough that I can kind of get used to just multiplying the scalar times the constant. This guy here, this is the same as the integral of x to the -5 dx, because we don't have an integration rule yet for anything that looks like this, but I can use the power rule here. So I add 1 to the exponent. That's going to give me x to the -4. I'm going to divide this by that new exponent and add my constant of integration. Or better yet, how about -1 all over 4x to the 4th plus a constant? I rewrote this as such. Looks a little cooler that way. This guy again doesn't look like it, but this is a power rule because this is x to the 1/3 dx. So I add 1 to the exponent. That's going to be x to the 4/3, and I'm going to divide by 4/3. Now, of course, we know that when you divide by a constant, a fraction like that, the same as multiplying by the reciprocal. So this is 3/4 x to the 4/3 plus our constant of integration. And as I mentioned before, this is like a constant here, like a 1. So when you integrate dx, you get just x. So this is just 1x or x plus your constant. Okay, now we're ready for this problem where we have a sum. What I'm going to do here is I'm going to write this as 9 dx plus the integral of 8x dx. Now I don't normally do this every time, but I wanted to show you how the sum, the integral of a sum is the sum of the integrals. So now, what do you get when you integrate 9? You would get 9x plus, and 8x, that would be up to 2 over 2. So it's 8 times x squared over 2. That'd be 4x squared plus your constant. See, I normally jump from here to here. I just go one term at a time. Here's another good example, one term at a time. This would be up to 5 over 5 using the power rule. So this is 6/5 x to the 5th. Up to 3 over 3. The 3's would cancel, so plus x to the 3rd. Up to 2 over 2 plus 1/2 x to the 2nd. And then when you integrate a constant, it's just the constant times x, so minus 9x plus your constant of integration. Good thing that we don't have to put a plus c for every term. One c kind of carries it for it all. Now here I have a trig function. Now when we take the derivative of cosine, we get negative sine. Excuse me. When we take the derivative of cosine of x, we get negative sine. So remember, we're reversing this. What are we taking the derivative of to get cosine? Well, it'd be sine, because the derivative of sine is cosine. So this is going to be 2 sine x plus your constant. So when we integrate cosine, we get negative sine, derivative of cosine, we get negative sine, but when we integrate cosine, we get positive sine. Now this guy here looks like a problem because of the square root of x in the denominator, but I would probably take the time to write this as x over x to the 1/2 plus 1 over x to the 1/2 dx. Break up my integrand like that, and then I could rewrite this as the integral x over x to the 1/2 as x to the 1/2. 1 over x to the 1/2 would be plus x to the negative 1/2 dx. Now it's not so bad. One term at a time. So I add 1 to this. If I add 1 to 1/2, I get 1 1/2 or 3/2. So divided by 3/2 is the same as multiplying by the reciprocal 2/3 x to the 3/2. Add 1 to this, I get 1/2. Divided by 1/2, same as multiplying by 2. So that's going to be plus 2x to the 1/2 plus my constant. Okay. Now put equal signs in between your steps here. Some of you guys have a tendency to just assume that I know what you mean when you don't put them in, because you put one line on after the other. But put your equal signs in, please. Now this guy here, he looks like trouble, because I don't think I have an integration rule that has this kind of an expression in it. I have ones with cosines and sines and such, but nothing quite like this. I'm going to rewrite this as the integral of negative, I'm going to write this as the cosine of x over the sine of x times 1 over the sine of x dx, which I'm going to write as the integral. Let's see, 1 over the sine of x is cosecant, so I'm going to write this as negative cosecant of x, and then cosine of x over the sine of x is the cotangent of x dx. Well, didn't we have a rule for that just a little bit ago? Let me find my rules. Yes, as a matter of fact, we did. When you integrate cosecant x, cotangent x, you get negative cosecant x. Well, I have a negative already in there. So I could bring that negative, like a negative 1 out in front, and I would get negative 1 times negative cosecant of x plus a constant. Well, if I bring this out in front, well, a negative times a negative is positive, so this is just equal to the cosecant of x plus a constant. This guy is also different looking, because I have what looks like a composite function here, but I'm going to go ahead and square this out. I'm going to write this as the integral of y to the 4th plus 2y squared plus 1 dy, and then this would equal 1/5 y to the 5th up 3 over 3 plus 2/3 y to the 3rd plus y plus a constant, and there's my answer. Now you will get better at this as you practice it. It looks like I'm just buzzing right through these because I've had a lot of practice with it. So this guy here, again, it's a rational. That's a problem right now. So I'm going to rewrite this. I'm going to divide t squared into both t to the 3rd and 1, and I'm going to get the integral of t plus t to the negative 2. 1 over t squared is t to the negative 2 dt. So up to 2 over 2 would be 1/2 t squared. Up to negative 1 over negative 1 would be minus t to the negative 1 plus my constant. Now notice here also, I didn't mention it before I actually did the problem, I'm using a different independent variable instead of x. I'm using the independent variable t. That's fine. It doesn't matter. The rules work the same way. So this is 1/2 t squared minus 1 over t plus a constant. Now, I get this answer this way. Sometimes if you look in the back of the book, they'll actually take the first two terms, get a common denominator, and write it as a single rational expression that way. But this is fine. Nothing wrong here. This guy is going to be problems because we don't have anything for a product like this, but we have them for sums and differences. However, this is the same, remember, as x to the 1/2 times x plus 5 dx. So if I distribute, I get the integral of x to the 3/2 plus 5x to the 1/2 dx. So this is going to be up to 5/2 over 5/2 is 2/5 x to the 5/2, up to 3/2 over 3/2, which is like multiplying by the reciprocal of 3/2, 2/3, so that would be plus 10/3 times the 5, x to the 3/2 plus my constant. Now, that was a lot of different kind of looking problems. There's some good examples also that you can find, hopefully some of them in the notes, some of them in the textbook as well, if this is not enough. It just takes a lot of practice. All right, we're going to try to finish up a little bit here with some application problems. Now, as I mentioned before, when we solve a differential equation, we're solving for y, and if there's a plus c in the answer, that's called a general solution. But if we have additional information, we can find a particular solution, and I don't want to say an exact one, but one for a particular case based on that information that's given. And in that case, we typically have some information which I like to call the initial condition. Sometimes just extra information. So here's a differential equation, dy dx equals 3x squared minus 4. We're going to find the particular solution, knowing that 1/8 satisfies the solution to the differential equation. So first things first, let's find the general solution. So that means I'm going to rewrite in terms of the differentials. I'm going to separate my variables, write it in terms of differentials, integrate both sides. I get y equals up to 3 over 3 would be x to the 3rd minus 4x plus my constant. Now that's not my answer because that's a particular solution. This 1/8 ordered pair satisfies this solution. So if I plug 8 in for y and 1 in for x, you see how I can solve for c? I get 8 equals, now that's going to be what? Negative 3 plus c, which is going to give me c equals 11. So my particular solution is y equals x to the 3rd minus 4x plus c, which is plus 11. If I give you a different bit of information, you might end up with a different a particular solution, because as we mentioned, the plus c means there's infinitely many possibilities, a whole family of solutions here, but in this case here's the second cousin, so to say. All right, one more here, and I'm going to do it the long way one time here for you to kind of give you an idea of what's going on. It says a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. So that means that v sub 0 is equal to 64, and it means that s sub 0, the initial height, is 80. It says find the position function given the height s, giving the height s as a function of t. Well, here's what I'm going to show you. I'm going to start with acceleration, because it's a ball being thrown upward. My acceleration is gravity, or negative 32 feet per second per second. I'm going to integrate, and I'm going to get that my velocity, I integrate the left side, I get velocity, because remember the derivative of velocity is acceleration. Integrate the right side here, I'm going to get negative 32t plus a constant. Now here's where this bit of information comes in. My initial velocity is 64, so that means v of 0, which is negative 32 times 0 plus c, is equal to 64. Well, that means that c is 64. So now I can put the 64 right in there. So now I have v of t is equal to negative 32t plus 64. Let's try this again. Let's integrate to find position. The integral, the antiderivative of velocity is position because the derivative of position is velocity. So s of t would be equal to, now I integrate this side with respect to t, so up to 2 over 2 is negative 16t squared plus 64t plus another constant. Since I know my initial height is 80, I can say s of 0 is 80, so that's negative 16 times 0 squared plus 64 times 0 plus c is equal to 80. Well, that's 0 here, so that means c is 80, and that goes right in here, and there is my position function. Plus 64t, and then plus c is 80. Now remember, we had the formula for position for a free-falling object as 1/2 gt squared plus v sub 0t plus s sub 0. We had that in pre-calculus, and we talked a little bit about it in this class. There's your gravity, that's your negative 32, that goes there, times 1/2, that's the negative 16. There's your initial velocity, 64, there it is. There's your initial position, your 80. So I could have come up with this just by plugging in the information, but I wanted you to see how the antiderivatives give you that information. Now it says, when does the ball hit the ground? Because it's thrown upward at 64 feet per second with an initial velocity of 80. When does it hit the ground? Well, it hits the ground when s of t is 0. So I'm going to set negative 16t squared plus 64t plus 80 equal to 0. And I'm going to solve this and see if I can answer my question. I think I'll divide through by negative 16 since it's divisible into all three terms, and then I can factor. I get t minus 5, t plus 1 equals 0. I get t is 5 and negative 1. Well, we're not looking at negative 1 seconds, not unless we're in the twilight zone there. So we're looking at 5 seconds. So when does the ball hit the ground? The ball hits the ground 5 seconds after release. And there's the answer to that problem. Now, there are all sorts of applications that are coming. There's your very first one here for integration. So look this stuff over. Ask questions if you're unsure. But as always, practice, practice, practice.